I will begin.
This reminds me of psychotic.
I see. I don't understand, but I see. I will.
You need to dock him some points based on his his choice of art.
Yeah,
Artistic skill.
I have no comment. I will begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today, Lord. In my prayer, Lord Jesus. Amen. So I'm going to talk about the pullback.
She's just a girl.
And so here's the definition. If F is a mapping from M to N, a smooth map, and omega is, let's say, a K-form on N, then the pullback under F of omega is the K-form on M, defined by F pullback omega of P. We feed it in vector x1 out through vector xk, all right, k vectors input. That's going to be omega of F of P acting on the push forward under F of x1 out to the push forward under F of xk. For each P in M and x1 through xk in TPM. Moreover, in the case k equals to 0, we have a smooth function, and the pullback is simply accomplished by composition. So in the case k equals to 0, we have that the pullback of omega at P is simply defined to be omega composed with F at P. So in the case of a 0 form, we don't act on vectors because this is just a function, and the pullback just amounts to function composition. Now, if you read Rentland defines the pullback first by its properties, and then he uses that to define the push forward. So, which is kind of backwards from what we've done, obviously. And also, like, there are certain parts of Rentland which are very advanced, and so, like, if you don't understand a couple pages in Rentland, I wouldn't Rentland. It's okay. All right, like, there's a place or two he dabbles in much deeper mathematics. So hopefully my notes are, more understandable, even if they are at times with some typos and the intentional misspellings, of course. Now, the properties of the pullback are as follows. We have pullback under F of A omega plus B tau is A times the pullback of omega plus B times the pullback of tau. All right. So we have, and that's for A and B, a real number. And omega and tau, K forms on N. And we also have the property that the pullback of omega wedge tau is the pullback of omega wedged with the pullback of tau. All right. And then, so that's number 1. And this is number 2. And then finally number 3. The pullback of the exterior derivative of omega is the exterior derivative of the pullback of omega. So pullback and exterior differentiation commutes. Again, as I was saying, if you read Rentelen, he takes these essentially as defining conditions for the pullback. And he kind of goes from there. In fact, that's not a bad, in fact, operatively speaking, that is actually how I behave in this course. I use these properties to calculate. That is the honest truth. I don't really almost ever use this definition directly. I mean, I could, right? There might be a place for it. Certainly to understand the proof of these properties, which is given on page 189 of my notes, you'd need to use the definition. But looking at these proofs, I really don't want to write them because they're knee deep into the muck that I've been explicitly trying to stay out of, namely the construction of the tensor product as an anti-symmetrized sum over permutations. All right, so it's like it's got the evil thing. The thing that's beyond our course is there, but it's basically that's necessary in order to sketch the proof in a nutshell. You can define the pullback on the tensor product just in terms of essentially just composition, and then so if you already have a sense of how that works on the tensor product, if you just do that over the anti-symmetrized tensor product, and then you un-anti-symmetrize it, that's essentially how the property is proved. That's a summary of the proofs on page 189. But anyway, I want to show you how we can actually calculate pullbacks with these properties. All right, so that's what we're going to do. Before I even do that, though, and this is what I meant to start class with, and I just forgot, I want to just say a word or two about what we're doing and how we do it. All right, so like this is a digression from my current purpose, but so this is just a remark. Given a vector, all right, and so we could say this, a vector field, so here's the notation for vector field, this symbol on M. So this would be a vector field on M. And you're given a coordinate chart, X, right? Then we can expand V in the coordinate chart, all right? We can expand the vector field like this. We can say, well, that's really the sum I equals 1 to, let's say, M of V upper I partial xi. And I'm intentionally not writing the point dependence because I, in fact, do mean this as a vector field equation, all right? The V upper I are functions, and the partial xi are vector fields that are defined on the chart domain, right? How do you find VI? Like, what's the procedure for calculating VI in this context? It's very simple. If we take V and we act on a function, then what I get, by definition, of like function addition, if you will, or operator addition, I suppose, is this, all right? So, by the way, comment. If I have V in the smooth vector fields over M, and if I have F is a smooth function on M, then VF is another smooth function on M. In fact, we could characterize the smoothness of vector fields by this criteria, that when you feed it a smooth function, you get out a smooth function. This is one possible way to carefully define smoothness of a vector field. The other way has to do with building a chart structure on the tangent bundle and taking sections of that and stuff. And it turns out that that's equivalent to this, but that is a lecture or two worth of material, so let's not do that. So this, though, how do I calculate VI then? Which F do I look at? The coordinate chart, right. So to find VI, to select VI, look at V of X upper I, right? Or maybe up, let me make this a J. See, because then if I have V of X upper J, I'm talking about the sum I equals 1 to M of V upper I, partial xj, partial xi. That is the Kronecker delta ij, the natural enemy of the finite sum, and it just leaves us with V upper I. My bad, V upper j, which is the free index here. So if you want to calculate the components of a vector field, act on the coordinate chart that's at play, all right? Likewise, if alpha is an element, so I'm introducing some notation here because I didn't have a notation last class, but it occurs to me it would be good for us to have a notation. Because we have a notation for the cotangent, like the cotangent space, and we have a notation for the tangent space, but we didn't have a notation before for a continuous assignment or a smooth assignment of those objects together along a, along some region. So that's a vector field, this chi-m and now chi-star m. This is a covector field, or what I'd like to say is it's just a one form, right? Alpha is a one form. So again, we have alpha, we can write it as the sum I equals 1 to m of alpha sub I dxi, right? Where dxi, as we talked about last time, is dual to the coordinate derivations, right? Now, how do I find alpha I? What's the formula for that? Well, if you calculate alpha of partial xj, right, that's going to be the sum I equals 1 to m of alpha sub I dx upper I of partial xj. And again, these are dual, as we talked about last time, Kronecker delta ij, lo and behold, alpha sub j, right? Once more, if, how do you, smoothness, what does it mean, smoothness? Well, if we have V is a smooth vector field on M, and alpha is one of these guys, one of these forms on M, then alpha acting on V is going to be a smooth function on M, right? Take a differential form, feed it a smooth vector field, get out a smooth function. This is how it works, all right? What's the question?
Is Kronecker delta ij equal to Kronecker delta ji?
Yes. Uh-huh. It is symmetric. Very true. All right. So the reason I'm saying this is something you can fall back on. If you're not sure how to calculate something, take it apart into pieces, right? Like, and again, I'm distracting from my current lecture, but you'll forgive me. If I had f of xy equals to, I don't know, x squared plus y squared and xy, right? And I'm saying f is a mapping from R with xy coordinates, and let's say that this over here is AB coordinates, right? And I want to calculate the push forward of an arbitrary vector, what's the push forward under f of a partial x plus b partial y, right? So, by the way, this star is yet another notation. I know, it's obnoxious, right? So let's say f star of p is, let's say, dfp, okay? Yet another notation for the push forward the upper stars are pullbacks, the lower stars are push forwards. I don't like this notation that much, honestly, because I think it's really, for me, when I was starting, it was very hard for me to like process star versus star. It just all muddled together. Like I kind of like this notation better. Other people use a T here for like the tangent vector. That notation you'll find in Jeff Lee's book. But anyway, okay, so what's that? Close the parenthesis. It's closed.
Talking about when you wrote remark given the thingy, top of the right of the first whiteboard, and the smooth that can get it on in. You just didn't close the parenthesis. She's just
I don't even see it. Like oh, that.
Honestly, it'd be funny if you left it.
No.
I do.
Or add like a pointy bracket.
So, so the point here is that the point is that dfp of a vector, right, is supposed to be an element of the tangent space at f of p, you know, of n, let's say. Let me call this thing n, and let me call this one over here m, all right? So what's the basis for vectors in my codomain? You know, it's the span of what? It's the span partial partial A, partial partial B, right? So that means that dfp of v has to be something like dfp of v acting on A, partial partial A, plus dfp of v acting on B. Oh, my bad. I did something really, really unhelpful here. Like,
Wait, you use this as constant?
I used the A and B in two wholly different ways. Not good. All right. All right. Tell you what. Let me use U and V here. I'll use U and V here, and so I'm gonna switch out for U and V for the coordinates, and I'll stick with my A and B for the coefficients for the input here. Oops.
Now there's more B's.
Well, fine. I've got a fix for that.
Mix with a mu.
It's true. Just capital it.
There we go. All right. So, how do we can calculate these, right? What's dfp of v acting on u? What was our man? Well, that's from rats. What was our definition? Was v of what? V of u of f, right? But u of f, that's just a fancy notation for the first component function. So what we're looking at there is v of x squared plus y squared. On the flip side, dfp of v acting on v, we're looking at v of little v composed with f, which is the second component function, which is xy. Right? My v is equal to a partial x plus b partial y, right? That was given. I'm telling you, we're setting that you know, that's what we're saying. So what happens here? I get what? Partial x hits it. I get what? I get 2ax plus 2by. Yeah. And this one I get AY plus BX, I think, right? I'm just doing plain old partial differentiation with x and y and partial x and partial y at this point, all right? Put it all together. What's the push forward of f at the, push forward of f acting on v? I got, 2ax plus 2by partial u plus ay plus bx partial b. Now, to be fussy, and I've dropped the point dependence. I could put the point dependence back if you wanted, right? So v is at the point P, right? But these guys over here are at f of P, right? And if I was going to be faithful to that, well, I think I've already got the x and the y there. So like my P is x comma y, so to speak. I mean, I don't know. If you want to, I could put P as like P1, P2. That might help. I don't know. So like 2a P1 plus 2b P2 partial u at, I don't want to write it, but I'll write it. P1 squared plus P2 squared P1, P2 plus parentheses A P2 plus B P1 partial B at f of P. All right, I've written enough. What happened? Have I gone back to A's and B's again?
Yeah.
Oh man, look at that. That's interesting. It's just like I really want to use A and B for coordinates, don't I? I mean, what's wrong with me? And this is why we definitely can't do the double feature. Like, it's not going to work. We're going to try to meet tomorrow at noon. If you guys can come, I understand. If you can't, I understand. But I'm not sure where. I mean, we'll try to do it here. See if we can. Yeah. What's that? Can you invite friends? Are they annoying?
I'm not sure yet.
Okay, yeah.
Well, if
Will you be recording it?
I'll be recording, yeah.
Is it more likely that you'll invite them?
I don't know. Okay, so this is just like, this is a way to calculate. You can kind of, you don't have to do it all at once. See, like finding components this is a manageable calculation, right? Yeah, you could sort through all of this in terms of chain rules and such, but I find this to be a convenient program of calculation. The other way to do it, of course, is to embrace the formula I wrote over there and do a matrix multiplication and then sort through the meaning of the coordinate map and all that. Like, there is a shortcut way to do this faster, but this is a way. All right, enough about that. Let us get back to the pullback. Well, we've got this example. Let's calculate a pullback. Consider like alpha equals to, I don't know, u squared dv plus v plus 2 du. All right. Let us calculate the pullback of alpha, where f is the mapping previously given, right? So we're calculating the pullback of u squared dv plus v plus 2 du. All right. And what I told you guys is we're not going to use the definition. We're going to calculate by the properties. Like, it's just the best way. Okay, so first of all, this is the pullback of u squared times the pullback of dv plus the pullback of v plus 2 times the, so you might put a wedge here, but the reason I'm not making wedges is because they're zero forms, right? It's scalar multiples, so like You could put wedges if you wanted, but it's kind of not necessary in this particular context. Now, of course, what does the pullback of u squared mean? I mean, this is also the pullback. Well, let's just get to the point. This is u composed, well, it's u squared composed with f. Maybe I should write it as u composed with f squared. That might make more sense. And then we're talking about the exterior derivative of the pullback of v. Over here, we're talking about, again, v plus 2 composed with f, I think. And then here, this is the exterior derivative of f pullback u. All right, so just a reminder, we should look at this as uv. That's basically what informs the calculation. So you want to think about u equals to x squared plus y squared, and v equals to xy. All right. So u composed with f is what? U composed with f, this in particular is x squared plus y squared. But I'm squaring it, yeah? And then I'm talking about the exterior derivative of the pullback of v. Well, the pullback of v is xy. And then my v, oh man, well, composed with f. So this is actually xy plus 2, I believe. That's this piece. And this here is the exterior derivative of x squared plus y squared. So what I'm doing, all right, let me just kind of demystify what I'm doing. I'm simply plugging in. If you really just take a step back and look at what I did, at the end of it, after you get past my property steps, all I really did was put u equals to x squared plus y squared and v equals to xy and plug it into the form. That's all the pullback does, is it substitutes the defining coordinate formulas from the codomain back into the domain. And so we can work this out, of course. X squared plus y squared squared. And this is, of course, y dx plus x dy plus xy plus 2, 2x dx plus 2y dy. And you can clean it up, you know. So we've got x squared plus y squared squared times y plus 2x times xy plus 2 all times dx plus x squared plus y squared squared times x plus 2y xy plus 2 close big parentheses dy. There you go. Pullback. That's the pullback. Let's do another. Let's let beta equal to u du wedge dv. Let's calculate the pullback. What is it? Aha! Pencil sharpening. I should have. So the pullback of beta, let me just get straight to it. What's u equal to? X squared plus y squared, right? And then we take the exterior derivative of x squared plus y squared, and we wedge it with the exterior derivative of xy. And this is x squared plus y squared. You got yourself 2x dx plus 2y dy wedged with y dx plus x dy, which gives you an x squared plus y squared, parentheses, 2x squared minus 2y squared dx wedge dy. We could factor the 2 and clean it out, but there it goes. That's the pullback of that particular 2 form. It pulls back to a 2 form back in the xy space. This is pullback. So it seems it seems a little intimidating at the definition level, right? But when you actually get into examples where I actually have you calculate something, it's actually not that bad. I have a more grand, glorious example to show you guys. These examples so far have really not been very preachy. There's no kind of hidden message. It's just a sample calculation to get us started. The next example, I'm trying to get across an idea. Can I erase this? Good, okay. What's what? The vector, I'm just saying the vector at P. I'm pushing forward the vector at P to this vector over here at f of P. So the push forward goes from one point in the domain to the image of that point in the codomain. So we're pushing the vector from one spot to another.
Pushing a vector that's attached to that point, or pushing the point?
Pushing the vector that's attached to the point. We don't push the point.
Okay.
Yeah. All right, let me see if I can find my handy dandy example here. Let's see here. I think this one's good. This one's pretty simple, but it's not a bad example. Example 4, I guess. Let's look at g as a function from R4, where I'm going to use coordinates x, y, z, w. And I'm going to let it map over here to 3-dimensional space with coordinates r, s, t. And my mapping, g, of x, y, z, and w, it's going to be equal to x plus y plus 2w, y plus w, and x plus y plus 2w. All right. So I want to calculate the pullback of the top form in RST space. I'm going to calculate the pullback of the top form in the RST space. So here, this is my R, this is my S, this is my T, right? So dr is dx plus dy plus 2 dw. ds is dy plus dw. And dt is dx plus dy plus 2 dw. So this particular function's linear. So, I mean, honestly speaking, this is kind of overkill for this problem, but I think it's good because it's simple to understand. All right, so what's the pullback? The pullback of dr, wedge ds, wedge dt, all right? It is the pullback of dr wedged with the pullback of dt wedged with the pullback of dt, good grief, ds. Sorry, I lost track of my letters here. So RST, pullback, pullback, pullback. But what is the pullback? Pullback means at this level simply, this means, well, the property of the pullback, this is the differential of G composed with R, you know, wedged the differential of G composed with S, wedged the differential of G composed with T. And these, I think I have to do the other way around, right? Yeah, I just did it back. I'm sorry, my bad. T, yeah, thank you. R composed with G, S composed with G, and T composed with G, which is just a fancy way of saying the first component, first, second, and third component functions of G. Of course, we already have those right here. That's what we calculated already. So just put those down here. We got dx plus dy plus 2dw wedged with dy plus dw wedged with dx plus dy plus 2 dw. Zero. Actually, no. You know, there was a time I thought that, and it really confused me. Because it does seem like, I know, right? It seems like that should mean that it's 0, but it doesn't mean that. Unless I've got a typo up here.
So it's x plus y plus zw.
Well, let's calculate. Let's work it out. See what happens here. So we got dx wedge dy plus dx wedge dw. All right. Plus dy wedge dw plus twice dw wedge dy. That's everything I get from the wedge product of the first two. And I have used, of course, that like dy wedge dy is 0, and you know, so that's this piece, all right? So I still have to take the wedge product with what? Dx plus dy plus 2 dw. I mean, I kind of want you to be right. I kind of want it to work out to 0, but I don't think it does. So, all right. Let's take the wedge with dx to start with, all right? So using the dx, 0 on this, 0 on this, but we got dy wedge dw wedge dx plus 2 dw wedge dy wedge dx, right? That's from my dx terms. Let me use some color. All right. Then let's use the y. Yeah. So the first term is 0. The second term gives me dx wedge dw wedge dy. And then this one also has a y in it, so that's wedges to 0. And this one also has a y in it, so it wedges to 0. So the double underlined y term just gives rise to this one non-trivial term. And then finally, last, that we got plus, I'll bring the 2 out front, dx wedge dy wedge dw. Let's see, then there's a w in this one, and that one. So that's it in terms of the contribution of the third, the trice underlined w. Is there any commonality between these terms?
Make it work.
First one's just dw, dy, dx. Because you can switch the first term and then it goes negative and takes away 1 and 2.
So you say I've got dw wedge dy wedge dx to start with from these two terms? How about these?
Those.
Is our goal to get him dx, dy, dw?
Yeah, that ends up.
Like two
Yeah, that ends up being
two terms, can't
This is also dx, dy, dw? I mean, these are the same. It's xyw, xyw, but the last, so this, yeah, plus dx, wedge dy, wedge dw, right?
It's 0.
It is 0.
Aw, man.
Which it should be because you have
Well,
two of the same vectors that you originally get.
well, hooray.
I should have monster wrong.
Only if you draw more bows on my figures.
Deal.
Huh.
Yeah.
Is that right?
It would have to use z at all.
Well, yeah.
Yeah, that's kind of silly.
Yes.
Because dt equals dr, so you end up with a dr wedge dr. Yes, that's right.
Yeah, I mean, we could have just done that. I just didn't want to believe it. But yes, you're right. There's a much easier and less stupid way to do this. To see that it's 0.
It's nice to know it is there.
Man, what'd I do? That's what I get for preparing for class.
Just weighing it more, huh?
Why don't you just make,
I really should.
why don't you just make t like
I think I had dy wedge dw wedge dx minus dx wedge dw wedge dy. And I had chalked myself into those being different choices of 3 letters, but obviously they're not. Good grief. Okay, so yeah. What does this mean? What does this mean?